this is about homework number 6. Homework number 6 had a rather interesting error in it on my part. I wrote a question for you that didn't entirely make sense. So sorry about that, I'll explain that at the end. I think it didn't make sense in a rather interesting way though. Now question 1 was about making the multiplication table for the group of symmetries of an equilateral triangle. I'm not going to go through that because, as I said, you can look it up on Wikipedia to check that you got the right answer. Question 2 was about the symmetries of the square acting on these 4 lines and resulting in some permutations of the numbers 1, 2, 3 and 4. And at some point later we'll see that what we've actually done, because each symmetry of this square has resulted in a permutation of the numbers 1, 2, 3, 4, what we've actually made is a group homomorphism from D4 to S4, because we took each symmetry of the square results in a permutation of 4 numbers. So let's see what permutations result. Now you can fill this in quite quickly by observing, first of all, that this line number 1 can only ever end up on either 1 or 3. It's never going to turn into a diagonal. And 2 can only end up in 2 or 4, and likewise, so 2 and 4 are always going to be diagonals. They're never going to end up in 1 and 3. So this column is all going to be 1s and 3s. This column is all going to be 2s and 4s. This one's all going to be 1s and 3s. And this one is also all going to be 2s and 4s. So now let's have a look. Obviously, this is the identity, so this fixes everything. Now, then you can have a look and see what 1 does. Well, in the first rotation, it's going to go to 2. What am I talking about? It's not going to go to 2 at all because it's a diagonal. First rotation, it's going to go to 3 because we're rotating by pi by 2. So it's going to go to 3, and then it's going to go back to 1, and then it's going to go back to 3, and then it's going to go back to 1. And similarly, 3 on the first rotation is going to go to 1, and then 3, and then 1, and then 3. And similarly, 2 is going to go 2, 4, 2, 4, and 4 is going to go 4, 2, 4, 2. Now let's look at the reflections. When you reflect in any particular line, the line itself is obviously going to stay fixed. So B1 fixes 1, B2 fixes 2, B3 fixes 3, and B4 fixes 4. Now, each reflection also fixes the line that's perpendicular to the one that we've got. So B1 is also going to fix 3, B3 is also going to fix 1, B2 is also going to fix 4, and B4 is also going to fix 2. And then in each case, the other 2 lines will get swapped. So we swap these 2, and we swap these 2. So that may not have been how you worked out what this table was, but I just thought I'd show you another way. Instead of just working your way down and working out what each permutation was separately, you could fill this table in by patterns quite quickly. Now, the next question was to say, what's the orbit? What's the orbit of 1? Well, where does 1 ever end up? 1 can only ever end up on 1 and 3. And what's the stabilizer of 1? Well, what are the elements that fix 1? You can look at that in this table. I mean, you can find the orbit of 1 by looking down this column and seeing all the numbers that appear in this column, right? And to find the stabilizer, you find all the places where 1 stays on 1. So that's those places, which is A squared, B1, and B3. And finally, the orbit stabilizer theorem tells us that the size of the orbit of 1 multiplied by the size of the stabilizer of 1 has to be the size of the group G if G is finite. And look, here we've got 2 elements, here we've got 4 elements, so we get 2 times 4, and here the number of elements of D4, well, you can count them in this table, there are 8 of them, so this does satisfy the orbit stabilizer theorem. Now the last part of this question was about turning this square into a circle, so that now we've got, I wonder if I can turn this into a circle, so now we've got a circle instead. And at first sight, it does look like the symmetries of this circle will still act on the lines 1, 2, 3, and 4, right? However, that's not true. This group, the group of symmetries O2, does not act on these lines. rotation by a very small angle. Rotation by, say, this much is going to leave our line 1 sitting there. And that's not any of the lines that we're supposed to be acting on. So rotation will leave this line sort of in a void that's not part of this set, and that means that this group doesn't actually act on this. You might say, well, could I just define the action to be that rotation along some small angle doesn't put our line here, but puts it somewhere else. And you could actually use the axioms for a group action to show that it's not possible for this group to act on that set. Now, this was an unfair question to be set because it doesn't really act on this set at all. But some people said, well, it doesn't contradict the theorem because the theorem only holds for finite groups. And that's true, but there is also an infinite version of the orbit stabilizer theorem, which you did in PMA 112, which says that there's a bijection between the size of the orbit and the cosets of the stabilizer. Now, it looks like you can find the orbit and stabilizer of number 1 still, because you might think, well, the orbit of 1 is now 1, 2, 3, and 4, because now when it's a circle, we can do any rotation to make the line 1 end up on any of these things. And it looks like the stabilizer still has the same 4 elements that it had before. It's going to have the identity, rotation by pi by 2, and reflection, and a couple of reflections. We want reflection in this line, which counts as reflection by pi by 2, and we want reflection in this line, which counts as reflection by pi by 4. So it looks like, certainly these are the elements of O2 that fix this line. And certainly, among these lines, the symmetries of O2 can make the line number 1 move to all of those lines. But this would give us 4 times 4, which is, of course, 16. And this has nothing to do with anything, really. And the reason it has nothing to do with anything is because it's not a group action at all in the first place. So the orbit stabilizer theorem only holds if every single element of your group can do something to the set in question. I'll repeat that. Every single element of your group has to do something to the set in question.